Bismillahirrahmanirrahim. Binary operations. So today we talk about binary operations, and they are very important in all of the mathematics, but like especially in group theory, because you need a binary operation to define a group, a ring, or a field. So for a ring, you need two binary operations. Even for a field, you need sort of one. Yeah. So let's define definition. It SBS 8 a non-empty set, a binary operation on S is a function from S cross S into S. So roughly it takes two elements and then produced a one. So you can say for any ordered pair x comma y inside S cross S, where x comma y are from S, a binary operation assigns a third number of S. A binary operation assigns a third, like so if these x comma y are two members, the third member of S. Now, another point is if, let's say, star is a binary operation on the set S, we write x star y where x comma y are in S. So instead of writing this x star y, instead of, you can say, instead of writing star of x comma y, the since image of star is a subset of S, we say that S is closed under star. As we say, Z is closed under addition, since if we add two integers, we obtain an integer. But like natural numbers is not closed under subtraction, because if we subtract two natural numbers, we will not always get a natural number, but a negative number. Sometimes you can get that. So, yeah. Now we have to define a mathematical system using these binary operations, using the binary operation. So, definition. What is a mathematical system? Number 1.6.2. The name of this definition is mathematical system. Okay, so we say that a mathematical system is an ordered tuple, n plus one tuple, like this, s comma star 1 star n with n binary operations, where s is a non-empty set and star I is a binary operation on S, where I is 1 to up to n, and S is called the underlying set of the system. So these can be binary operation can be 1, 2, or up to n. Okay, perfect. Definition. One point 6.3. Let S with a star is a mathematical system, then number 1, star is called associative if for all x, y, z in S, x star y star z is x star y star z. Number 2, star is called commutative if for all x comma y in S, x star y star x. So the mathematical system can be associative, and then for a mathematical system, star can be associative and commutative, right? Let's say we have an example that consider a mathematical system Z along with the binary operation addition. Since addition of integers is both associative and commutative, since addition of integers is both associative and commutative, then addition is both associative and commutative for Z. Well, okay, right. Example, let's say this is one. Another example is that we take a non-empty Z, it's not phi. Let S be the set of all functions on A, then we can define this S set as follows, that it contains f, given that f is a function from A into A. Since composition of function is a function is a function, we know that since composition of functions is a function by theorem 1.5.11. So S with the composition is a mathematical system. Right? And we know by theorem 1.5.13 composition is associative. Composition is associative, like for F, G, H, and S. F compose H. G compose F compose H is G compose F compose H. Right. You can also define example like three says that let M2 R define the set of all 2 cross 2 matrices over R and we define this M2R as a set which contains A, B, C, D matrix such that A, B, C, D are from real numbers. Let's define let this denote the addition of matrices and this denote the usual multiplication of matrices. Multiplication of matrices now since addition slash multiplication of 2 cross 2 matrices over R is a 2 cross 2 matrix over R. It follows that addition and multiplication is a binary operation on M2R. Hence, M2R with addition and multiplication is a mathematical system. Note, addition is both associative and commutative in this context, and multiplication is associative but not commutative. Perfect. Now we give the example for which the operation is neither associative nor commutative. So example 4, we have a mathematical system Z along with the binary operation minus, where this denotes subtraction, the binary operation of subtraction on Z. Then 3 minus 2 minus 1 is 2, which is not 0, is 3 minus 2 minus 1. And 3 minus 2 is not 2 minus 3. So is neither associative nor commutative. Now, let's define a convenient way to define a binary operation. And we know a way to do that. So, and it's given by Cayley. So let's define the Cayley table. So let's say we have S is a set which has A, B, C, 3 elements. Define star on S by the following table. Operation table, not table. So the table is star A, B, C, A, B, C, A star A is A star B is B, A star C is C, B star A is B, C star A is A, sorry, C, B star B is A, B star C is A, C star A is B. Oh, okay. C. CBA, A, and then B, B, B. Now, this is a particular way to like compute. So this means what? This means that A star A is C. A star B is A star B is B. And A star C is A. Then other way around, B star A is A. B star B is also A. B star C is also A. Now C star A is B. C star B is B. And then C star C is C. This is the convention, and then or that we have defined this table. So this is the result. This is a result. These are the results of when we use the binary operation A star A, this is the result, A star B, this is the result. So the intersection of these rows and columns will give us the result when we use the binary operation. Okay. Right. So then we can give the definition again. So definition 1.6.8, which says that let S comma star be a mathematical system and element E inside S is called an identity of this mathematical system if for all x inside S, we have the property that E star x is x, which is also x star E. Right. Then using this definition, we can write an example. And now we have a set S, which contains E, A, and B. And star is a binary operation. So let's compute the table for these elements E, A, B, E, A, B. Now, E is the identity in the set, and its product with E star E is A, E star A is A, E star B is B, A star E is A, and this is B. Now, what about itself? A into A is A into B is A, B into A is A, and B into A, B is A also. Now, this we have to define or consider that how we get. So this is this is still undefined, but we know about these. Okay, so we note that E star A is A star E, E star B is B, which is B star E, and itself E. Thus, E is an identity of S comma star. Perfect. Now, in this way, we can find out the identities for the mathematical systems. So let's say we have another example, which is one which says that for a mathematical system, okay, let's number those. So we had this example number 2. For example number 2 about identity function is an identity element of this mathematical system. This is part 1. Part 2 is in example where we talked about the mathematical system 3 or matrices. In example 3, the 0, 0, 0 matrix is an identity element for the mathematical system M2 or R with addition, and the identity matrix is an identity element for the mathematical system M2 R with multiplication, right? Now, the most important thing is, which we will talk about in the theorem, is that if there exists an identity for a mathematical system, that identity is unique. There will not be any other identity. So, theorem says 1.6.11, an identity element brackets if it exists of mathematical system S with star is unique. This is the theorem. Let's prove it. So let's take E comma F be identities of S with the star. Now, since E is identity, E star A is substituting F for A we get E star F is F. Now F is an identity. Now F is an identity. And so A star F is A for all A in S. Substituting E for A, we get E star F is E. Then, so let's say this is 1 and this is 2. From equation 1 and equation 2, we get E is F. Hence, an identity element is unique. An identity element is unique. Let's talk about one exercise. Which of the following are associative binary operations? So, which of the following are associative binary operations? 1. Integers with a star, where x star y is defined as x plus y minus x dot y for all x comma y in z. 2. Reals with a star, where x star y, x star y is maximum of x comma y for all x comma y in R. Reals with a star, where x comma y is defined by absolute value of x comma y, x plus y for all x comma y in R. How to define which of them is associative? Let's try 1. So we know to show the associativity, we need to show that we don't need to show this property. And now we know that x star y is nothing but x plus y minus x dot y star z. And if we open this further, we will get x plus y minus x dot y plus z minus x plus y minus x dot y into z, right? And if you open this, this will be x plus y plus z minus x dot y plus z minus x dot y minus x dot y minus x dot x, x dot z minus y dot z plus x dot y dot z. And similarly, x star y star z is also equals to x plus y plus z minus x dot y minus x dot z minus y dot z plus x dot y dot z. Thus, x star y star z is x star y star z. Hence, star is associative for the first one. In two, we have x star y is max of x comma y. So we know that x star y star z is going to be max of x comma y star z. And this is going to be max of x comma y if you apply again, then that will be max of x comma y comma z. And then if you just do this, then it will be max of x comma y comma z. And then if you do this more, then it will be, you can also do that in the other way around. So that will be max of x comma max of y comma z. And this you can write x star max of y comma z, and this is nothing but x star y star z. So hence number 2 is associative. Also, number 3 says that for two reals, if x star y is mod of x plus y. So number 3 says, let's take two numbers 2 star minus 3 star 6, and this will going to be 2 plus minus 3 mod over star 6, and this we can write is 1 star 6, and this will be 1 plus 6, which is 7. Now, and 2 into 2 star minus 3 star 6 is going to be equals to 2 star mod of minus 3 plus 6. And that is going to be 2 star 3. And that is going to be 2 plus 3. That is going to be 5. So not equal. Hence 2 star minus 3 star 6 is not equal to 2 star minus 3 star 6. So star is not associative. That's it. We'll talk about introduction to groups in our next lecture series. But before that, I have some other application problems and applications to talk about in this group theory for beginners lecture series. So I'll probably talk about that. Thank you so much for watching. Please do subscribe for other videos. Thank you.